Okay, so hi everyone. Thank you for being here. This is joint work with Zelia Rad and Victor Vafiadis, and it has to do with verifying programs that have locks. So the first question that might pop to mind is this: why locks? Why bother with this particular class of programs? And there are actually a couple of reasons why we care about them. First of all, coarse-grained locking is probably the most widespread form of synchronization. And there are a couple of testaments to that as well. There are programming languages such as Java, which even provides syntactic support for it. For example, if you declare the methods of a particular class as synchronized, then they will all share the same lock. But also modern hardware provides lock elision support, which means that hardware manufacturers actually recognize this as a commonly occurring pattern. Now, the second reason why we care about locks is that actually verifying programs that have locks is hard. Now, this is specific to verification techniques for concurrency, but what this basically says is that it's harder for these techniques to verify programs that have locks than programs that do not have locks, or it's harder to verify a program with a coarse-grained locking scheme than a program with a fine-grained locking scheme. And to see an example of this, consider a fine-grained hash table, which means that we have a concurrent hash table and we use one lock to protect each bucket, and we try to verify it using one of the state-of-the-art stateless model checking tools, which the first two talks talked about. So roughly what these techniques do, as the previous speaker said, is that they enumerate interleavings, right? So if we take this fine-grained hash table and a state-of-the-art stateless model checker, this is more or less what we get. So we have a fine-grained hash table, and for 4 or more threads, the stateless model checker verifies it basically instantly. But then if we have a coarse-grained hash table, meaning that we have one lock to protect the whole hash table, these are the results we get. So the same model checker only finishes for 5 threads in less than 2 minutes. And for 6 or more threads, it needs more than 4 hours, so it times out. And this is a bit counterintuitive, right? Because one would expect that when you use more synchronization, when you use a coarse-grained locking scheme, you expose less behaviors of the program. So the stateless model checker should be able to verify it faster. And of course, this leads to the question, why is this the case? Why is it harder, for example, to verify a program with a fine-grained locking scheme than a program with a coarse-grained locking scheme? To answer this question, I have to take a step back and explain how stateless model checking works a bit. So stateless model checking basically enumerates all the interleavings of a program. And because this number, the number of interleavings, gets very fast, very quickly, we usually combine with partial dereduction. And what partial dereduction tries to do is it tries to avoid exploring some of these interleavings if an equivalent one, up to some commutation of events, has already been explored or will be explored in the future. So for example, if we have this program where x is in SLA0, and the first thread is reading from x, and the second thread is writing to y, then the naive stateless model checking algorithm would explore 2 executions, one where the first thread executes before the second, and one where the second thread executes before the first. If we combine stateless model checking with partial dereduction, then the partial dereduction algorithm would make the stateless model checker only explore 1 execution because these 2 instructions commute. They are accesses on different memory locations. Now, if we have this program, however, where we have 2 programs acquiring the same lock, then again, stateless model checking will naively explore 2 executions. But if we combine it with partial dereduction, now we also get 2 executions. And this is because operations on the same lock do not commute. This is because of the way they're modeled. They're actually modeled as compare and exchange instructions that have to succeed. But even intuitively, you can think of that if the first thread acquires the lock first, then it succeeds. If the first thread executes first, then it acquires the lock first and it succeeds. And if the second thread executes first, then it succeeds. So we have to explore both of these scenarios. And while this doesn't quite answer the question why it is easier to verify fine-grained hash table, although it does give a good hint, I have to explain, I have to give another example. For example, let's see this program where we have n threads in parallel reading x. And again, according to what I said before, the stateless model checking algorithm will explore n factorial executions. We have n instructions that they can be interleaved in n factorial ways. And if we combine it with partial dereduction, then these instructions commute. They will all these accesses will read 0 no matter when they're executed. Now, if we take the same program and we wrap these accesses in critical sections of the same lock, like this, then again, stateless model checking naively will explore n executions. In this case, because we have n mutually exclusive critical section. But also stateless model checking with partial dereduction will explore n factorial executions. And this is because operations on the same lock do not commute. And in this case, this is problematic because the accesses within the critical section, so these accesses, the read of x, actually do commute, and no matter how we execute these critical sections, these reads will always be 0. So what actually happens is that locks inhibit partial reduction. And in the example that I mentioned before with the coarse-grained hash table, if we protect the whole hash table with the same lock, even if we have clients accessing different parts of the hash table, just because the operations of the lock can be to protect the hash table, not commute, this leads to an exponential blowup. And what we propose for this problem is LAPER, which is a lock-aware partial reduction algorithm that basically lifts the existing partial reduction techniques to the critical section level. And LAPER is able to exploit independence at both instruction and critical section level. We actually prove that LAPER is sound, meaning that it explores no false positives, that it is complete, meaning that it explores all program behaviors, and that it is optimal, meaning that it explores exactly one execution per equivalence class, where the equivalence classes are defined by the underlying partial reduction algorithm. So in the case with the n parallel reads before, there's only one equivalence class because all the executions are equivalent. We also built this algorithm on top of the GNMC framework, which is a dynamic partial reduction framework that works for a variety of different memory models. So this is not just for SC, but also works for any memory model that satisfies a few basic assumptions. And we've also shown that LAPER can explore exponentially fewer executions than state-of-the-art model checkers in both benchmarks with coarse-grained locking schemes and fine-grained locking schemes. And I'm going to show you these results at the end of the talk. So I'm going to first present how partial reduction roughly works on background, then explain how we improve on that, and then conclude with some results. Right. So in general, we can represent equivalent interleavings of a program with graphs. And in general, all the executions of a program can be represented with a set of graphs. So if we have this program here where x and y are initially 0, and we have the first thread writing to x, the second thread reading from x, and the third thread writing to y, then all the interleavings of this program can be represented by these two graphs. In these graphs, the nodes, for example, this node, correspond to instructions of the program. So this means write to x the value 1. And the edges represent relations between the nodes. The PO edges, the black edges, are program order edges. These connect the events of the same thread or the initializer events to the first event of each thread. And the green edges are reads from edges, which show where a particular read is reading from. So in this case, this read reads 0, the initial value, and in this case, the read reads 1 from the first thread. Now note that this program has 6 interleavings. It has 3 instructions that can be interleaved in 3 factorial ways, so 6 interleavings. But what we want to do, and what is enough, is basically enumerate all these graphs, because we have many interleavings being linearizations of the same graph. So what partial reduction tries to do is just enumerate these graphs, and these represent all the interleavings. And let's see how this is actually done for the same program as before. What partial reduction does is basically a modified depth-first search. So we start with an empty graph, then we add the events one by one. And when we can add an event in more than one ways, we just pick a random way and backtrack later. So in this case, I'll just add the events from left to right. We first add the right of the first thread. Then this read can either read 0 or 1. We pick one option. Here we picked 1. And then we push the other option to a stack to backtrack there later. Then we add the event of the third thread. And this concludes the first execution. Now we backtrack, and we restore the graph in the previous state where this, but we make this read 0. And again, we continue the exploration until the graph is complete. So we add the instruction of the third thread, and this concludes the exploration of this program systematically. And let's see now how the same approach, the classic partial reduction approach, would handle locks. So if we have this program where we have 2 threads reading x within a critical section of the same lock, then the classic partial reduction technique would enumerate these 2 graphs. Note that in these graphs, locks have read semantics. They actually have compare and exchange semantics, and unlocks have write semantics. So in this execution, this read reads the initial value, which represents the first lock acquiring the first thread acquiring the lock first. And the second thread reads from the unlock of the first thread, which means that it executed after the first thread. And in the second execution, it's vice versa. So let's see how these are actually generated by the partial reduction algorithm. Again, we start with an empty graph. We add the events one by one. We first add the events of the first thread. There is nothing so very interesting so far. And then when we add the lock of the second thread, we'll make this read from the unlock of the first thread. And then we add this special backtracking point there for this lock, because the second thread can also read the initial value. It can acquire the lock first. And I'm going to explain why this is a special backtracking point later. Then we keep going, we add the events of the second thread, and this concludes the first execution. Now, when we backtrack to this point, the thing that we definitely have to do is remove these two events, since we're restricting the graph to the previous state, but we actually do something more. We remove these events, but we also remove the events of the first thread, and we block the first thread intuitively because the second thread succeeded in acquiring the lock, so the first thread cannot execute until the second thread releases the lock, right? So we keep exploring. We add the events of the second thread, and when the unlock is added, then we make the read of the first thread read from the unlock of the second thread, so the first thread is unblocked, and then we conclude the exploration. Now, the exact exploration procedure here is not important. What I want to show you in this slide is that the classic partial reduction algorithm explored two executions, these two executions, in both of which both reads of both threads read 0. And the only reason why we explored two executions was because of a backtracking point that we have for a lock operation and not for any read. So basically, this was the reason that we explored two executions. And what we propose for this problem, what Laper basically does is very simple. We say that locks are going to be unordered. Locks will not have any special semantics. And then if we have the same program as before, then Laper will only explore this execution. Note that in this graph, locks have no incoming RF edges, and locks have no outcoming RF edges, and both read 0. And of course, to generate this execution is trivial. We just add the events one by one. There's no alternative option for any of the events in this graph. And then we end up with two critical sections that are completely unrelated. And we can trivially generate this execution. And of course, we can extend this procedure over for 3 or more threads. It doesn't really matter. So what I'm going to show you next is how Laper would handle a case where the lock ordering actually matters, where we actually have to explore all orderings because we have critical sections that do not commute. So if we consider this program, where the first thread is writing 42 to x and y, and the second thread reads x and y, then in this case, if the second thread executes after the first, it will read 42 for both reads, and if it executes before the first thread, it will read 0 for both reads. So what Laper needs to do is that it needs to generate these two graphs. In the first graph, we have both reads reading 42, and in the second graph, we have both reads reading 0. Now, these are the executions that Laper must generate, and it also must not generate this execution, for example, where we have the first read reading 42, and the second read reading 0. And it must not generate this, of course, because this violates mutual exclusion, which is the whole point of the locks. And this not generating such executions is much easier with the classic partial reduction algorithm, mostly because the locks and the unlocks have semantics, which exclude some of the inconsistent options, and you get that for free. So in this case, we have to be a bit more careful. So I'm going to show you how Laper actually does this. We start, again, by adding the events of the first thread one by one. There's nothing interesting so far. We also add the lock of the second thread. And then when we add the read of the second thread, we pick one option. So we pick 0, for example, and we push the other option to the stack. But note that since we pick this option, since this read of x is now reading 0, this actually creates an ordering. And it means that the critical section of the second thread must have executed before the critical section of the first thread, because otherwise this read would have read 42. And this is important because in the next step, when we add the read of y, we need to take this induced lock ordering into account, and the read of y will only be able to read 0, not 42. Thus, we avoid creating any inconsistent execution. Of course, this concludes the first exploration, and then even when we backtrack and we make this read 42 from the first thread, this will also create an ordering, and this means that the critical section of the second thread must have executed after the critical section of the first thread, and we take this ordering again into account in the next step when we add the read of y, which in this case will only be able to read 42. So in general, as soon as we create a particular lock ordering after adding one event, we need to take that ordering into account in the next step when we add the rest of the events of the critical section. Now, of course, all these examples that I've shown you so far are trivial, but by applying the same technique to more elaborate locking schemes and more complicated data structure, we get significant performance benefits. So I'm going to start with some coarse-grained data structures. Our tool is the green one, Laper, and it's built on top of the GenMC tool. On the x-axis above, we have number of executions, logarithmic and below we have time in seconds, and in the x-axis in both graphs we have the number of threads. So as you can see, Laper is much faster and explores exponentially fewer executions than GNMC, in this case, of the coarse-grained set. Two comments that I have to make for all the benchmarks that we've used are that these benchmarks that I'm showing you have both readers and writers, because if they had only readers, then Laper would trivially explore in one execution. So there are actually critical sections that do not commute. And also, whenever we needed an implementation of a linked list, we picked the implementation of the linked list that is used in the Linux kernel. So we're actually verifying code that is deployed in production. Then the next benchmark is a coarse-grained binary search tree. The results are similar. And then we have a coarse-grained hash table, which is the same as the one that I showed in the introduction, where we have GNMC only terminating for 5 threads, while Laper still is much better. What's more interesting, however, is that even for fine-grained data structures, where we use, for example, some hand-over-hand locking schemes, Laper also manages to outperform GNMC. In this case, we have a fine-grained set, again, implemented over a linked list. And even though we have clients actually targeting locks of different nodes in the list, just because all clients will serialize at the entry point of the list, at the sentinel node, GNMC has to order all these lock acquisitions, while Laper doesn't, and this is why Laper is faster, even in the case of a fine-grained set. Similarly, for a fine-grained binary search tree, GNMC has to order all these lock acquisitions on the root node of the tree, even though we have clients trying to access the locks of different nodes of the tree in completely different parts of the tree. Well, Laper doesn't have to do this. And finally, for a fine-grained hash table, both tools explore the same number of executions, and in this case, Laper is actually slower because it actually has to compute this induced lock ordering at each step, while GNMC basically gets it for free because of the semantics that locks and unlocks have. So there are more stuff in the paper. I encourage you to read the paper. There's a detailed description of the algorithm. There's a formalization of this induced lock ordering that we have, and we also have more benchmarks and evaluation. The gist of the benchmarks is that Laper can be exponentially faster, while only polynomially slower when there are no critical section commutes. And in summary, I've presented a lock-aware partial reduction algorithm that can exploit independence at both instruction and critical section level. It is sound, complete, optimal, works for a variety of different models, and can be exponentially faster in programs with coarse-grained and fine-grained locking schemes. Laper will soon hopefully be available on GitHub on GNMC's page. And as future work, we would like to extend the same idea to transactions or other synchronization idioms. Thank you.
So there is plenty of time for questions.
Yeah, so thanks, Michalis. Just an observation. If I think back in Magnus's talk, I suspect that their saturation method is pretty much what you're doing with the locks, and you guys should probably already be able to handle this independence of locking sections.
I mean, I guess that even with in your approach, that locks they're not commuting, right?
Well, they could commute. You could make the release a read and the acquire a write and force a read from between the two. And then you would be able to commute. Yes, but you have to
impose this functionality usually because you cannot have two locks reading from the same write, which makes them not commute.
Well, no. So you would have a release being, so the release would be a read, right? And then you already know that it's going to have a unique local observation, a unique local acquire to read from. Anyway, let's, yeah.
I can ask you a question?
Yeah, sure.
So what you're suggesting is modeling just the release as a read of the write. But this doesn't work with our scheme out of the box, because what you're doing then is that you're excluding some of the possible read from, such as having the release read something else than its own lock. So our scheme is not sound with this. This is not, yeah, exactly. but this is required for the algorithm to work. We could do something like we could add what they are doing. I mean, it's similar to saturation, but it's more rules. But it does require some extra work. It's yeah.
Anyway, thanks to both.
Are there other questions? Comments?
Yes. It will be what?
Will be the default.
It won't be a default. It will be some switch. So if you have a course and a program that has like it has locks, or you suspect that you have a course grain locking scheme, you can enable or disable. I mean,
So let me ask then my question differently. What is the overhead that you have when you don't have locks?
if you don't have locks, there's no overhead.
It's just that you want to be fast when the locks are of the...
If you suspect that you have a coarse grain locking scheme, that something like this, you're using locks very conservatively, then this will probably yield performance benefits.
Okay, so unless there are more burning questions, then I suppose we should wrap up this session. We should thank Michalis first.
Thank you.